Now, I would like to invite Professor Dr. Callum to deliver his speech.
Okay, thank you very much for that introduction. First of all, my apologies for my late arrival at this meeting. I had some connection problems, which hopefully are resolved now. I'm just trying to work out how to do the share screen part because the display has changed and I cannot find it. So perhaps someone can help me because it was there a minute ago. There we are, I found it. That's good, right. Okay, be with you in a second. So there we are, and I just have to go to there. I hope everyone can hear me. Slideshow, display settings. There we go, right. Well, I hope everyone can hear me. If not, perhaps you can send me a message. Okay, so today I'm going to talk about some of the environmental properties of wood. It's a very topical subject at the moment. We're living in very strange times, as I'm sure we're all aware, with the coronavirus, which is causing so much disruption in the world. And I hope that we're not forgetting that we have a serious environmental issue caused by human activity in the planet, economic activity, which is leading to a continual increase in carbon dioxide concentrations globally, which in turn is leading to global warming and climate change. This is probably the most serious problem that we're facing, although coronavirus is certainly a very serious problem at the moment. The levels of carbon dioxide that we're seeing now are unprecedented. If we go back over 800,000 years or even 1 million years, the levels that we're achieving now through anthropogenic emissions have not been seen. So we're in a very uncharted part of the climate system. It's extremely unpredictable what's going to happen, but the only thing we can predict is that we will be facing severe changes to agriculture and other human activities. So it's important that we do something about this. These are the levels of emissions have really taken off since the 1950s, very much linked to increased economic activity. And the great challenge is going to be how are we going to reduce these emissions, but still maintain a level of economic activity so that we can keep people healthy, we can keep people educated, and we can maintain social stability. We're obviously not going to solve all the problems today. The area we work in is timber technology, and I've been concentrating very much on the built environment for many years now and the use of timber in the built environment. And if we look at a plot which shows the global CO2 levels, emissions by sector, we see that the built environment itself, just the construction part, the materials and construction, is responsible for 11% of global CO2 emissions. So there's a lot we can do about CO2 emissions by changing the way that we make buildings, how we construct them, and the materials that we use in order to produce them. Indirectly, we will also be affecting the building operations part of this. So as we make buildings more efficient and the building operations emissions decrease, consequently, the building materials will become more important. This is what the EU plans for the next two or three decades, how we're going to reduce emissions so dramatically without having serious effects on our economies is something I'm not sure that has been fully addressed yet. Even the effects of coronavirus and the shutting down of economies, I don't think we're going to feel the effects of that fully until next year, possibly the year after. And it's that kind of intervention that we're going to have in economics in order to make a difference with CO2 emissions. But luckily, the area we work in, using timber in construction, we're able to maintain high levels of economic activity. We're able to house people, And we're able to do this while simultaneously storing carbon dioxide. And there's been quite a lot of work that's been done on this. I'm not going to give a literature review today. It's not difficult to go out and find many papers that show how we can do this through the use of timber in construction. But there's also a lot of information out there which says the opposite. Quite often you find that this information has been funded through the cement or concrete industries or the steel industries. But there are counterclaims for every claim that we make saying that the use of timber in construction is a good thing for the environment. You will find counterclaims that say this is not the case, that carbon stored in wood products is substantially less than being claimed, but it is essential to account accurately for carbon dioxide that is being emitted. And there's many, many publications out there which are claiming that the carbon substitution benefits of the use of timber are overestimated. What I'm hoping to do today is to demonstrate that there is an effect, there is a carbon substitution benefit, and there is a storage benefit, but we have to account for this correctly. So these are the sorts of things that we're facing in the UK, how the UK cement industry aims to reduce greenhouse gas emissions by 81% by 2050, which is a good thing. I'm glad that they're producing such things, but when you read the detail, you find that they're not going to be able to do this without using carbon capture and storage. And there's very little investment going into carbon capture and storage at the moment. The advantage of using wood is not just through product substitution, which I'll talk about first in this talk, in which by using wood in a functional unit, we actually have lower GWP emissions. But we also have the carbon storage benefits, which will be the second part of the talk. And we also have at the end of the life, the recovery of inherent energy. I don't propose to talk about this, but it's an important aspect. There aren't many materials that are used in construction that are derived from atmospheric carbon dioxide and from which we can recover the stored solar energy in them at the end of the life cycle. So product substitution. If we look at the global warming potential of 1 kilogram of timber products, there are many, many environmental product declarations out there which contain environmental information. It's quite easy to go out there and get this information. The first thing that you'll find if you're looking at global warming potential is that very often you have a negative number. And the reason for that is because the environmental product declaration has included both the sequestered carbon, which is a minus number as far as the EPD goes, and also the emissions that are associated with producing this material, which is a positive number. And when you add those two numbers together, you end up with a negative number. So what I've had to do with these analyses of environmental product declarations is separate out the emissions from the stored carbon. There are very good reasons for doing so. The reporting of GWP still is quite commonly reported as negative numbers in timber EPDs, but the global warming potential in terms of emissions is now being separated out from the stored carbon, which is a step forward. And it's very important that we do treat these separately. If we look at the emissions of a range of wood products, solid wood is on the right-hand side, fiberboard on the left, we see there's quite a range of emissions associated with these products. It's very hard to pin down one number that belongs to one particular product. What I've been attempting to do in analyses that have followed on from this original study is to see if that there are characteristic values that we can associate with products. Generally speaking, the embodied energy and the global warming potential of a product will increase with the amount of processing, so that wood that is hasn't been dried will have a lower global warming potential than the wood that has been dried. When you saw it, the GWP will go up. If you make fiberboard, the GWP will go up. And what we attempt to do when we're doing comparisons between structures that are made from different building materials is we have to get these values, the GWP values, per kilogram of product, and use that to feed into the software, which is the inventory or contains the inventory of what is in the building. So just doing comparisons on a weight basis are not very helpful. Cement comes out looking worse than most timber products in this particular graph, but concrete comes out looking a lot better because, of course, concrete is diluted by the use of aggregate mixed with cement. Brick comes out looking fairly low on a kilogram basis. Huge variations in steel, which we'll look at in a minute, and only aluminium is definitely very much higher in terms of the carbon dioxide or greenhouse gas emissions compared with timber. But actually a plot like this isn't very helpful, and it's much more useful, in fact, to look at the functional unit, which I'll be talking about later. As I mentioned earlier, when we look at timber, most EPDs will include both sequestered carbon and the emissions in the same value, the same reporting value, and you always get a negative value, even with the higher impact materials like fiberboard. We still get more carbon dioxide is being sequestered in the wood compared with what is emitted in order to produce the material in the first place. It's nice to see such plots, but it's not very helpful if you're trying to do an analysis of the benefits of carbon storage. So here, this plot of some recently published environmental product declarations. I'm attempting to show the differences between the green timber, dried timber, and plain timber. What you should see is as the timber goes through more processing, drying and then planing, you'll get an increase in both global warming potential and the embodied energy. But what in fact we are seeing here is that there's quite a large variation in these values, and this will depend very much upon where the timber has been processed, what the electricity grid mix is, and many other factors, how efficient the kilns are, whether the kilns have been run off biomass, and also things like how's the emissions from the biomass, if a biomass kiln has been used, has that been included or not included in the GWP? And unfortunately, environmental product declarations aren't always very clear on this. So if you're using a specific one, it's important to be aware that a specific EPD is only for that product and isn't really a generic value necessarily for a whole range of products. And what I'm trying to do over time is to build up a database to look at numbers that are much more representative of a generic product. If we just look at one value here, this is for sawn green timber. It hasn't been dried and it hasn't been planed, and yet we're seeing a very large GWP, even though the embodied energy is not that much greater. This is just one example. What this particular EPD was reporting was a value for timber that is sawn in Australia, and in Australia the electricity grid mix has a very high fossil fuel contribution, and that's the reason for the high GWP here, even though the embodied energy is not much higher than the other materials in this plot. So this is the sort of thing you have to look for when you're looking at EPDs. Are the values representative? If they're not representative, is there an explanation for this? And sometimes there isn't an explanation. Sometimes somebody's made a mistake. So you have to be aware of this when you look at EPDs. Here's a range of values looking at steel. If we were going to compare a steel beam with a wood beam, what value of GWP do we use? We've got values as low as 0.5 kilograms GWP, carbon dioxide equivalents, per kilogram of steel. We've got values as high as 4.5. So what causes this huge variation? In this particular study, which I did for the Norwegian government, the values which are shown in pink, the ones that are Norwegian, the reason that those values are so low is because that is steel that is made using an electric arc process. That electric arc is fed by a hydro grid, so that it has very low GWP emissions. And also there are very high levels of recycled steel going into this furnace. Whereas by contrast, the one on the top right-hand side, this is for steel that is made in Poland, where the grid mix has a very high fossil fuel contribution, and also the steel is made from iron ore rather than recycled. So we have a much higher energy demand in order to make this. So there's no typical value for steel. We have to be much more specific when we're doing our EPD analysis or LCA analysis of buildings. We either have to use actual values that represent the materials that have been used in the building, or if we're analysing a whole sector, we have to use generic values that are typical of a particular product. We have to justify those values, and we also have to include the uncertainty. We have to be aware that these values could change, and we should include those uncertainties in the analysis, and that isn't always done. Similarly, we get the same kind of spread of data for different types of cement. I'm not going to go into the details here, but some of these values are actually suspiciously quite low for some of the cements, which makes you wonder if they've done the calculations right. But you can see that there are sort of clusterings of values for the different types of cement. So again, if we're using a cement in a concrete, what particular cement are we using? Where was it sourced from? What geographical region, this sort of thing. We have to be quite specific about where we've got our data from, or we have to admit that there is uncertainty and put that in the calculation. So for all that baseline data, all we're looking at here is comparing with things on a weight basis, but actually in order to make a proper comparison for the use of materials in buildings in our case, we have to use the correct functional unit. In a simple LCA study, we might look at a wall element which has got a given area of 1 meter squared, but it has to have the same function. So if we were looking at a wall, that wall would have to have the same insulation value so that it had the same operational energy requirements. So I'm going to talk about a study that we did fairly recently for the Climate Change Committee in the UK. And this was looking at the potential benefits for using timber in construction. There aren't that many studies out there where people have compared on a like-for-like basis. So the building which they've looked at from the point of view of constructing using timber or predominantly timber material compared with, say, masonry or brick or concrete is the same building. It has the same functional requirements, it has the same insulation, and it has the same thermal requirements. So the operational energy should be the same. So in this report, we looked at building archetypes. We used these values, which are, they were selected quite carefully to be representative of generic values for those particular materials. And we were very careful when we selected materials such as concrete or cement that we use values that the industry was comfortable with, rather than selecting values to make our data look better. So we feel that the analysis that we've done is representative. We used different building archetypes for which an analysis had already been done, looking at the energy requirements, the operational energy requirements for these different buildings. So we used the same designs and we just swapped materials such as wall elements for timber frame, for brick, or timber frame for brick and block, or masonry or concrete. So I'm not going to include the full analysis because it's quite complicated. So I'm just going to select some of the data that we took from this study. So here we have embodied emissions and we have sequestered carbon. And we separate those two out for reasons that I said already. The sequestered carbon is the carbon stored in the wood. That carbon will stay stored in the wood for as long as that wood is used in service, but eventually that carbon will leak out again into the atmosphere. So in that way, it is important that it's treated differently from the embodied emissions, which are the emissions that are released before that wood is put into service. So although one value may exceed another value if you take one from another, it's important that what you actually do is to deal with these separately in a different kind of analysis. So if we were just looking at the embodied emissions of a masonry house, which is the one at the top, I'll show these in a pictorial form in a minute, we can see that the embodied emissions for all the materials that have gone into constructing that house are 8.79 tonnes of carbon dioxide equivalent for a house. whereas the sequestered carbon in that masonry house is minus 2.86. And the reason that we have sequestered carbon even in a masonry structure is, of course, that we still have wood as part of the fabric of the house. It may form ceiling joists, it may form floorboards, doors, windows, roofing trusses, this sort of thing. So the buildings that we're looking at are typical for UK construction. They would vary in different parts of the world. This is what the analysis threw up. In this particular case, we're looking at the detached house of 117 square meters that I showed the drawing of. We looked at timber frame houses that were timber clad, timber frame houses that had a light cement-based rain screen cladding, and the more traditional block and brick construction, which is listed as masonry. So here we're looking at the different contributions from the different components in the materials, and you can see that, let's have a look, the plasterboard, I think the colours have come a bit strange here actually. We're supposed to be looking at the timber, which is the grey one at the top. Oh, sorry, the green one. No, I don't know which one it is. Oh, I'm sorry, the colours have changed. They're not representing what I'm expecting them to, so I'm going to have to move on. Here we have the sequestered carbon in the houses. And what I will show next is the difference between a timber house, a masonry house, a flat that's made from timber, in this particular case, cross-laminated timber, and a flat that is made using concretes. And here you can see that there are big differences in the sequestered carbon and the carbon that's emitted in order to produce the materials and build the house. So if we look at on the far right hand side, the flats that are made from concrete have got much higher emissions than the carbon that's sequestered in the house, because concrete is the dominant material. Timber is not used very significantly. With the timber flats that are made from cross-laminated timber, you see that the sequestered carbon far exceeds the carbon that's emitted in order to make the materials. You'll also see that the footprint, the carbon footprint of these buildings, the timber flats have a much lower embodied emission compared with the embodied emission of the concrete flats. And we see something very similar with the house as well. So if we take one value from another, which we're not really supposed to do, as I say, but just out of interest, we find that the timber dominated houses have a negative emission, whereas the concrete and masonry dominated buildings have got a positive emission. So they have a negative benefit. Basically, they are leading to global warming, whereas the use of timber in construction can lead to a mitigation occurring. But, and it's a big but, we have to bear in mind that the stored carbon will be released in the future, and I'll talk about that in a minute. So if we look at a typical year of construction in the UK, these are the kind of levels of emissions that we're seeing due to the use of different materials. And you can see that sawn and engineered wood and wood panels and CLT are responsible for fairly low levels of emissions, not just because they are lower emitting materials inherently when you make the functional unit, but also because they're not used as much. So if we were going to have a more of a positive benefit in terms of reducing emissions, what we should do is encourage the use of timber in construction and reduce the amount of reinforced concrete that's used. So it's not just the amount emitted per kilogram, it's the number of kilograms or tons that are used in a typical year. Whereas if we look at the amount of carbon that's stored in a typical year, obviously only materials that have a biogenic content results in stored material or stored carbon in the built environment. So there's quite a big difference in terms of the amount that's emitted. We're looking at 1.4 million tons from the concrete, and the amount that's stored about minus 0.8 of a million ton in the wood and about minus 0.4 million tonnes in the wood-based panels. So we all understand the concept that trees will absorb carbon dioxide during the process of photosynthesis, and that carbon dioxide will be stored in the material of the wood as cellulose, lignin, hemicelluloses. So the wood material is made from carbon that is derived from the atmosphere. And it's also very well understood that that tree can be felled, harvested, processed, and turned into a wooden structure. So that carbon storage is extended by putting the timber in a house, provided, of course, that that felling of a tree is replaced by the planting of a new one, and the forest continues to sequester carbon dioxide. So we need to have sustainable harvesting. At the end of the life, of course, that carbon that's stored in the wood will be incinerated, almost certainly, with energy recovery. That energy can be used to generate electricity, but that carbon dioxide will be returned to the atmosphere. So for that reason, we have to deal with the sequestered atmospheric carbon separately from the way that we deal with the GWP emissions. And just to go into this in a little bit of detail, it's not that complicated a concept, but stocks and flows do get mixed up when people report and talk about sequestered carbon. So very obviously, a flow is something that goes into or out of the stock. So a flow is a dynamic property of a system. The stock is a static property of the system. So if we have a flow that is larger than a flow that goes into the system that is larger than the flow that comes out, obviously that stock is going to increase. So if we were looking at carbon flows into the built environment, providing the flow of carbon into the built environment is larger than the flow of carbon out of the built environment, we have climate change mitigation. So that's a benefit. However, if we reach a situation where the flow out of the system is greater than the flow in, obviously that stock is going to decrease. In that case, if we were losing more carbon out of the built environments going in, well, that would actually have a climate change disbenefit. It would lead to global warming, because although that carbon has been derived from a biogenic source, it's now increasing, it's responsible for increasing the levels in the atmosphere. And it's for this reason that people have asked that EPD should report the sequestered carbon and the GWP emissions separately because of this property. In some ways, I think this has been pushed forward by industries that don't want sequestered carbon to be included at all. And that is wrong. Sequestered carbon needs to be included. It needs to be accounted for, and I'll explain why that is a bit later on. And we can also have a system where that we have a system where it's in equilibrium, in which case the flow into and out of the system is equal, in which case the stock doesn't change. So we're not having a climate change mitigation benefit, but we're also not having a global warming disbenefit either. So at some point, we are going to reach equilibrium in the built environment as we put timber into the built environment and increase those levels. At some point, the flow in and the flow out will equal each other. And mitigation will no longer take place, and the timber will act as a store. We have exactly the same with natural system, like forest, for example. A forest will reach a point where the trees are dying as quickly as new ones are growing, and that forest is now in a state of equilibrium. So all systems will tend towards an equilibrium state. So it has been suggested by some industries that the sequestered carbon shouldn't be included at all, because all you're doing is making a problem for future generations. We might be storing carbon now, but we'll be releasing it in the future. Isn't that just kicking the can down the road? So I'm just going to present a very simple model that I've created, which is looking at a carbon inflow into a system. And it's we're not using real data here, we're just using some assumed numbers. So we're looking at a system over a 500-year period, and we're looking at a carbon inflow of 1 tonne per year into that system. The system is going to start at 0, and we're going to look at how that system behaves as the carbon leaks out again. Now, in order to measure the way that the carbon is leaving the system, we have to create a function that is representative of the material. Quite often, people model this using an exponential function, and that exponential function is what's recommended by the IPCC, the Intergovernmental Panel on Climate Change. You can have different half-lives for material, but the problem with using a function like that is that most of the material comes out very early on and not later on in the life cycle, and that's not very representative of what's going to happen in the built environment, because you're not going to make a house out of wood and half of that wood's going to disappear within a couple of years. It's much more likely to take a long time frame, a long time period for that material to come out. So in order to measure this or to represent this more accurately, we use probability functions such as this. The particular one that I've been using is called a gamma function. It doesn't really matter what they're called. It's basically a distribution, and it's much more typical of what you might expect for a material such as timber in the built environment. Initially, very little of that timber is going to be lost back to the atmosphere, but over time, we're going to start seeing more demolitions, we're going to start seeing more replacements. And eventually, over a long enough time frame, all of that timber is going to come out of the system. So all of that 1 ton that went in 1 year is going to come out, but that's going to be distributed over a large number of years, depending on how stretched that function is. So if we do something like that, this is what we end up with. Because it takes time for that carbon to leak out of the system, we end up with a system that doesn't reach equilibrium until a certain period of time, a finite period of time. So in this particular case, I haven't shown what the actual function is, what the time frame is, but I'll show that in a minute. This system takes about 50 years to reach equilibrium, and it stores 30 times more in the pool than is going in each year. So what we're doing with using this as a way of mitigating against climate change is we're buying time, essentially. We're buying time because we're storing carbon over a time period. And during that time period, I would hope that we would make changes to the way that we generate wealth so that we can make a transition to a low carbon economy. So it's not a fix forever, but it's a fix perhaps for the next 100 or maybe 200 years, during which time we need to make this transition. So this shows the effects of a life extension. In the graph in the top left-hand side, we have a function which has got a typical half-life of about 25 years. And the one below that, on the bottom left-hand side, this function has got a typical half-life of about 100 years. So we're extending the lifetime of the product by about a factor of 4. And it shouldn't be a surprise to learn that the amount of carbon that gets stored is also increased by a factor of 4. And the time it takes to reach equilibrium also increases by a factor of 4. So we're extending the time to equilibrium from about 50 years to about 130 years, something like that. And we're increasing the amount of carbon that's stored in that pool by a factor of 4. So lifetime extension is a very important factor. If we're going to store carbon in buildings, in timber structures, we need to make those structures last as long as possible. And it's not just about structural integrity. A lot of things get replaced for aesthetic reasons. And Jakob was talking about that in his talk, why people replace timber quite often before it's reached the end of its useful lifetime. And quite often it's either for aesthetic reasons. It looks like something they weren't expecting. It might have weathered in a way they weren't expecting, or it might just be fashion changes. So in the buildings of the future, whether we make them from timber or other materials, we have to make them more adaptable. We have to make the buildings so they can possibly fulfill multiple functions over their lifetime, so that we don't have to build and demolish. We have to get away from this create and throw away aspect of our society. So using timber is a benefit. It will provide a benefit in terms of carbon storage, and it does provide a benefit in terms of substitution. But we also have to be aware of product lifetime, and we have to build timber buildings that last longer. Interestingly, as we're making a transition to a timber-rich built environment, we're going to have a growing market. And the effect of that is basically, for as long as that market is growing, we don't reach equilibrium. So that is a constant benefit in terms of climate change mitigation for as long as that market is growing. Now, clearly that market is not going to grow forever, because the built environment market is finite in size, and we have a finite capacity to produce timber from the forests of the world. But during this transition period, we get a benefit not just from the carbon storage that we're putting into buildings now, but because we're going to be increasing that carbon storage. So that's a linear increase, and that's what happens to the carbon stock over time. With a linear increase, we just don't reach equilibrium. Now, if we look at an exponential function, which is what economists are very fond of, the growth in GDP is an exponential function. If that material consumption is linked to the exponential function, then basically we end up getting some very silly numbers, because the growth in the carbon inflow will also grow exponentially, and it will definitely overwhelm the potential for forests to supply the timber. So I'm only showing this as an example of why we have to decouple our economic activity from materials consumption and energy consumption, because the earth doesn't have the capacity for absorbing our waste or supplying our needs in an exponential manner, because we live in a finite system. So that's what the carbon stock does with the exponential function. We end up after 500 years with nearly 4,000 times as much carbon stored in the system as goes in year one. But that's simply because of the exponential growth of that increase. So a non-sustainable system. So some very simple conclusions. The study that we performed for the Climate Change Committee of the houses showed that we get a double benefit. Substitution is a benefit because we have lower impacts from the use of timber as an alternative to non-renewable construction materials. So we have lower GWP emissions, and the carbon storage also has benefits when using long life products. You don't get the same benefits with short life products. So life extension is very important from the point of view of carbon storage. It's also very important from the point of view of reducing environmental impacts generally. So that's the website for the company. If you want to contact me and get me to try and explain that chart where the colours threw me off, I'm more than happy to do that. But I'm also more than happy to talk in much more detail about some of the things that I've been presenting today. So you can contact me through the website, or you can get me through LinkedIn just as easily. So thank you for listening, and thank you for your patience, and especially for accommodating me with my connection problems earlier. Okay.
Dr. Hill, thank you very much for your great presentation. We are very glad to see you here. Thank you very much for also your effort and valuable contribution to our Congress.
Thank you.
Do you have any questions for Dr. Hill?
Seem to be some delays, some sound issues. So. Nothing happening.
Thank you very much.
Okay, you're welcome.
Thank you. Thank you for joining us.